Okay, good afternoon, everyone. My name is Magnus Madsen. I'm a professor at Aarhus University. I'm a programming language designer, compiler writer. And today I will tell you a bit about the things we are working on. I hope to show you something new. Maybe also in the broader context, this question of how can programming languages move forward and how can we bring ideas from research into industry. So this is my hope at sort of contributing to that overall goal. Okay, so I assume many of you are familiar with imperative programming, object-oriented programming. I heard this used to be like a Java conference. And some of you may be familiar with functional programming. So today I want to talk to you about a new paradigm, a new upcoming paradigm that I think we're going to see more over the coming decade. Some are calling it effect-oriented programming. It also has other names. And to show you this, I also need to show you in a programming language that supports this, right? Like imagine if I wanted to teach you object-oriented programming. Well, I would need a programming language with support for objects, of course. So I will be showing the Flix Programming Language, which I work on. And one tagline could be here that if you love types, then you're going to love effects. And if you don't love types, then maybe effects will make you also like types. We'll see. Just before we get started, and while the last people are coming in, I just want to say this is not just my work. This is also the work of my team, my PhD students, Matthew, Jonathan, Andreas, and our programmer, Jacob. We've been working on this for several years, actually. We also have a growing community of open source contributors, maybe some future contributors among you. We'll see. And finally, this is a serious effort funded by the Danish government and other research funding agencies. And I'm not putting this slide necessarily to brag, but more to illustrate that we're actually trying to build a real programming language. So what I'm talking today about is not a prototype, it's not a toy, it's not a proof of concept. We actually want to build the whole thing. And that's something I'll also return to towards the end of the talk. But first, let's talk about effect-oriented programming. So what is this? So the point of an effect system is to try to capture the actions that a program can take. So when we are calling a method or a function, today maybe we know that it takes some arguments and they need some types and it returns something of some type. But what we cannot easily tell is that if I call this method, well, will it access the file system? Who knows? Will it access the network? Who knows? Will it modify some memory? And in fact, these kind of things should make us a little bit nervous because we build a lot of our software based on libraries developed by other people that we might not even know, and they also use libraries and so on. So it's kind of scary when you think about calling a method that someone else has written. So effect systems aim to get these things under control. And why? So one thing is that we can better reason about programs, so we can understand by looking at function signatures, for example, what can this thing actually do? We can also enforce that certain behavior is not there. So if there are scary things, dangerous things, unexpected things, we can rule them out. And finally, this is also a great enabler of compiler optimizations that are simply not possible without it. Okay, so maybe effect systems in one slide. If you have a function like f of x, it takes an argument x, and then it's going to divide by the getCurrentMinute. Well, if you have a type system, it might tell you that, well, x has type int, and f is a function from integers to integers. And that's fine. So you know, okay, I should pass in an integer and expect an integer back. Let's say that's the case. What it doesn't tell you, but that an effect system could tell you, is that, well, first of all, what if the current minute is 0? That's not good. Then you get an exception, division by 0, at least in some languages. An effect system could also tell you that actually, if you call this function passing the same argument, it might give different results. So it's not like incrementing a number. The result changes over time. It is non-deterministic. So just to repeat, the type system told us something about the shape of the arguments coming into the function and coming out. And an effect system tells us something about the actions that can happen. So in a programming language like Flix, we have types, but we also have effects. So for example, here we can write a function. It's called add. Takes 2 arguments, x of type int32, y of type int32, and it's going to return an integer. Okay, fine. Then the new part is that in addition to the return type here, there's this backslash, and then there's an effect set. Now here the effect set is empty. And this is a guarantee that this function cannot have any effects. This means that it cannot access the network, cannot delete your file system, cannot print to the screen. It cannot raise any exceptions either. In fact, if you call add with the same 2 arguments, you'll always get the same result. And this cannot be subverted. This is a property of the system. In the same way in Java, you cannot pass a string to a function that expects an integer, say. Okay, so in addition to types, we have these effect annotations on our functions. And here we're expressing, well, this one has no effects, so it's pure. This can get a little bit more complicated. It will get a lot more complicated in the next slides, but it's also necessary. So how many here of you are familiar with Rust? Or heard of Rust, let's say. How many have heard of Rust? Right. Okay, great. And then there's often this discussion of, is Rust a complicated language? And if Rust is a complicated language, then the designers did a poor job, right? They should have made it simpler. Or is it just because the domain they're trying to model, so this thing about shared memory and concurrent setting, is that domain just inherently complicated? And so to capture that, you need a more complicated system. And so I belong in the latter camp, right? That really what is happening is that languages like Java or JavaScript for that matter, well, they're just hiding a lot of complexity by pretending it doesn't exist, right? And then that just leads to bugs and crashes at runtime and these kind of things. And as we build programming languages that are more sophisticated, then we start revealing this sophistication, this complexity. So it's not really that these languages are badly designed or overly complicated. It's just that they necessarily have to deal with this complexity. That was just a side note. So I wanted to illustrate here that, let's say we want to write a count function, and the idea is I have a list of A. So in Flix, if something is lowercase, it's a type variable. So in Java, you would have some square brackets here with A. And if it's uppercase, we know it's a name type, like bool and list and int and so on. So anyway, so the point is it could be a list of students, right? And you want to count how many students have passed some exam or something. So you want a count function like this. Many languages have something like this. Now, since count takes a function argument, right? Maybe while counting, we're also, doing something. In Flix, we can actually specify whether some effects are allowed while counting. So in this case, I've specified that actually no effects are allowed, and then the count function also has no effects. This is a design choice, like in the same way when you write a function, you decide what the signature will be. In Flix, in some cases, we do this because then we can do the counting in parallel. Now, you cannot do the counting in parallel if there were some side effects. Imagine that you were printing something. And if I started doing the counting in parallel, then you would be printing in a different order. That's in the best case. In the worst case, there would be all kinds of things like race conditions and other invariants could be invalidated. So this is just to say that when you get some function arguments, we can enforce properties on them. Okay, so that was about the absence of effects. But for effects to be interesting, there should also be some actual effects. So the simplest effect in Flix is the I/O effect. It doesn't really have anything to do with the I/O monad, other than I/O just means, hey, I'm doing something with the world. That's what it means. So if you have a function here, say hello, you can call print. Println has the I/O effect, hence say hello must also have the I/O effect. So if you perform an effect, you call a function that performs an effect, then you yourself are performing that effect. Okay, great. Now I already said this, but if you try to lie, it will not work. So if you try to print and you say, hey, I actually don't have any effects, then the compiler will tell you, well, this isn't allowed. It's like a type error, except we call it an effect error. Right? So this gives you the same guarantees that you would expect from a type system. The world makes sense, right? You know, students and strings and URL objects are not the same. In the same way, pure functions, impure functions, functions with certain effects, well, they are not the same. They are not interchangeable. You cannot break this. Moving on to a more interesting example, an important example, perhaps one key point to take away from this is that often the effect of a method you write, function, will depend on the effect of something else. So for example, if you have a map function, so you might remember from another language, the idea is you have, like, let's say, a list of students, and you want to convert it to a list of their addresses. Well, then you can map a function over that list that extracts the address from each student object. Well, what if as part of that extraction, you're doing some effect? Maybe you are printing something, maybe you are logging something to a log file, I don't know, it could be anything. Well, to deal with that, there's a concept called effect polymorphism, and that means that, as we saw before, functions, they have effects on them, and now the effect of map here is EF, and that is the same effect as the function you pass in. So pass in a pure function, and the call to map will be pure. Pass in an impure function or a function with some effect, then map will have that effect. And this is how we're able to track effects through your program. I guess I give the example here. So this is a pure function. It's just multiplying and adding. So the effect will be the empty set of effects. I forgot to say effects in Flix are sets of effects, or these effect variables. Mapping with print, I mean, a little bit weird thing to do, but we'll have the IO effect. This, of course, is new and different, but there's actually not that much scary here. If you've seen, generic types before, this is kind of the same idea, now just for effects, and you see these things appearing in different places. Okay, so I have a few scary slides. This is one of them, but it'll make sense. So if we have two functions, f and g, and f is from a to b, and g is from b to c, right? So maybe we have a function from integers to strings, another function from strings to strings, then we can put them together, corresponding to just doing both things at the same time. Well, what happens when we have effects in that case? Well, each function will have some effects, ef1 and ef2. Well, the function we get out of it will just have the union. We don't want to use some fancy UTF-8 symbol, so we just use plus. So this means when you compose two functions, okay, then you get the union of the effects. So what we've seen is kind of that the language of effects are sets of concrete things. We've only seen I/O so far, but we will see other stuff. Then you can combine that with union, so you can kind of get bigger sets. But we also see it could depend on some variables, like with map, where it depends on the argument. Another thing we can do, which is kind of cool, is that, so how many have experienced like some error handling code itself crashing? Only one person? Really? Okay, good. So, wouldn't it be nice if our error handling code itself doesn't throw certain exceptions, for example? So this is the idea of effect exclusion. Here's showing it a very simple example, but still, we could have some exception handlers. So we're going to say on exception, then we're going to pass in some function that should be executed when an exception occurs. And this function should be allowed to do pretty much anything. Log to the log file would be a good thing to do, perhaps. But it shouldn't throw itself, because then what was the point? So in addition to union, we also have subtraction. So we can actually say you can do anything minus throw. So the handler cannot rethrow. If you try to pass in a handler that tries to throw, then it will not compile. This is actually more useful. There are many cases. I just picked one other. So if you've written a UI program, I don't know, Swing, JavaFX, and so on, maybe you heard this thing that you shouldn't block the UI thread. And why not? Well, it's because then the program gets white, or I don't know, like you press the button and the button is like stuck while you're waiting for the network or something, right? But there's no way, there's no way to, like, how can we guarantee that, right? It's up to you, right? And you don't discover until someone reports it. But the same idea could apply here. If we tag things that may block with some block effect, then we can say, well, when you register a mouse event handler, I don't know, so the mouse is moved, then it can do anything you want, but it cannot block. And then if someone tries to do something that blocks, the program will not compile. So you see here how we can use effects to, this was the thing about enforcing the absence of certain behavior or ensuring certain safety properties of our program, things we couldn't express before. Okay, so this brings us to an interesting question, and this is also a research question, so in the sense that I will say something about it, but I don't think there's like a single answer. So if you're designing a programming language, a question comes up which is like, what types should your language have, right? And so if you're in Java, you might say, well, I have booleans, integers, floating point, and then I have classes, right? And that's like what I have, maybe a little bit more. And if you're in JavaScript, then you don't have integers, right? You only have floating point numbers and so on. So there's this basic question of what are your base types, right? And this varies a little bit between languages, but there's sort of some consensus that you probably have a Boolean type and probably have a string type. But still, there's some variation along the edges. Now, when it comes to effects, because this is, I would say, more new, less developed, it's not so clear, what effects will come with your language. And so we're trying to answer this question, and I'll tell you what we've done, but it might not be sort of the final answer. This might require sort of more iteration and experience. But in Flix, there are 4 kinds of effects. So there are primitive effects. We've seen just one that was I/O. I'll show some more. Then there are effects exclusively related to mutable memory. So these are effects you will use if you have mutable memory, you have mutation. If you don't have mutation, then you will not see these effects. Then finally, there is something called, academic term, algebraic effects. Some people call it effect handlers. How many have heard of effect handlers? Great, so you will learn something new. So this is kind of, so really these 2 categories are the same, but it's just some come with the library, some are user-defined. And what I mean by that is that, class student, class person, that would be a class you write, not the Java standard library, right? But a class string, well, that's also a class, but it's written as part of the library. So there's this distinction that certain classes belong in the library and certain classes belong in your code. In the same way, certain effects will belong in the library and certain effects will belong in your code. So in Flix, we have just these 8 for the moment, primitive effects. And they basically mean sort of what the name suggests. So fsread means that you're reading from the file system. Exec means you're executing programs, like with a process or whatever. Network means you're accessing the network. There's a huge design space here because instead of having 8, we could have maybe 800 if you wanted to have them very fine-grained. We could also just have 1, I/O. I/O here is kind of the one that is everything that's not here, like printing to the screen. The attempt for the moment is to separate these into very harmful versus less harmful. So for example, if you think about, so how many have heard about like supply chain attacks, Log4j2, UA parser agent, these kinds of things, yeah, so some people, right? So the attempt here is to really distinguish between things that are very bad. So very bad is like when some library says, well, I need access to the network, and I need to read from your file system, and I also want to execute processes. So this is kind of the recipe for, taking all your data, all your GitHub tokens or your company secrets and uploading them, right? And so you hope that the library you're using for terminal coloring doesn't need the ability to execute, access the network, and read from the file system. That will be unexpected. Okay. Heap effects. So that was the second category. Oh, slide with a lot of text. I'll just explain. Some of you have probably heard like, oh, you should all do functional programming, like no side effects. It's like, just, write in Haskell, all your problems will be solved, right? And that's not the message I'm coming here with today. So I'm saying like, effects are fine. It's effectful programming, right? It's not pure programming. So you should just program with effects, totally fine. And the only thing I'm saying is, let's track them. So in the same way we track types, let's track effects. That's my message. Now, memory is a little bit special because consider some function you write, and you allocate a counter, you increment it a little bit, and then you return the count, right? Well, such a function is not pure in the sense that you are changing things. But if the thing you're changing, when it goes out of scope, right, if it goes out of scope before the function is over, then it is actually pure. So it's actually okay to do imperative programming with mutable things as long as you confine yourself to a scope. Yeah. So I just want to show you how that can look. So you're probably familiar with array list or things like that. So for example, if you have a mutable list, it's exactly like an array list. We just call it mutable list. Then there can be an operation like pop, right? So it's going to take the top element or the first element of the list and return it back to you. Here's an option in case it's not there. And then it says, oh, I have a heap effect in R. Well, what is R? Well, a mutable list has some elements that was our types, like student, person, and so on, but it also has a region. That's the lexical scope it belongs to. And then it says, okay, I'm doing some mutation that belongs to that scope. Okay, maybe an example will make it clearer. So check this out. I have a function here. I introduce a scope. So this we call a region. It's called RC. So within here, I can create mutable things. And I can mutate them. But by the end of this block, all those things better go out of scope, become unreachable. So I can create a mutable list of animals. I can add some animals here. Doing these things is having some heap effect in this region. So I have this effect here. And then I can print the last animal added, I suppose. Yes, so print some zebra. But the cool thing is, this heap effect here disappears once I got out of this region. So actually, this code only has the IO effect from printing. It doesn't have any heap effects. Give you another example. If you wanted to sort a linked list that is immutable, then a fast way to do it, a good way to do it, is to take that list and convert it into an array, a mutable array. And then you run quicksort on it, right? And what will quicksort do? Or merge? No, quicksort. Well, it will swap the elements around, right? It's changing it in place, right? You remember quicksort from back in the day. And then at the end, you take your array and convert it back to a list. Okay, sure, there's a little bit extra work here, right? But in O notation, it's the same. The cool thing is, this sort function is pure. You don't see any backslash here with some effects. So it's a pure function written in an imperative style. So you get to keep like the imperative programming style while still having the property of being pure as seen from the outside. Don't worry about the code, but the very same thing happens a lot. For example, toString, right? When you implement toString, what do? You create a string builder, and then you throw things into the string builder, right? Like appending things, whatever. And then at the end you say to the string builder, okay, now give me back the string, right? And the string is an immutable thing, and it comes out. So actually, such toString functions are pure. And now we can actually have that. So people who call toString know they always get the same thing back. The same with sort. Sort is a pure function. When you sort things, if you give it this list, you get the sorted list back. If you call it again with the same list, you get the same sorted list back. Okay, so we can be functional programmers, but we can use imperative style when we want. So we kind of get the best of both worlds. Because we can look at the sort function and see that it's not uploading our file system to the internet. Right? It has no effects. But inside it, there's a lot of mutation going on. But it's fine, because all that ugly mutation, those data structures disappear just before the function is returning. Okay, so we saw primitive effects. These are sort of the ground things, right? That you build things from, like, we saw network and these kinds of things. And then now we've seen heap effects, so they were related to mutable things. Now we'll see effects and handlers. This is a huge research topic. It's a little bit complicated, but somehow I'll introduce it in a few slides. So the key idea is this. You write one program, right? This is actually like a key idea in all of programming, right? You write one program and then you somehow parameterize it. You write one program here. You can think of it as one function, but it could be many functions calling other functions and so on. And then all your indirect inputs, I don't know if you're familiar with this term. I think it comes from testing, right? For example, the current time. That becomes an effect that you define. So for effect handlers, it's a bit like you specify some interfaces, and then later you're going to provide an implementation. But I'll talk about how the implementation is provided in a different way than you're used to. The same thing with indirect outputs. For example, writing to a file, you also express that as an effect. Okay? So if you did this consistently, and you could also do that in Java, right? It would be a bit like, you need to get all these dependencies in, right? There's dependency injection, whatever, right? So you get some interfaces in with all the stuff that you need from the outside. What is the current time, for example? And if you want to write to something, like a log file, then you also have like an interface that allows you to do that. And then if you wanted to test it, you could provide, mocks and so on, right? So you can kind of already do this in Java, right? You would just have methods or constructors that are very long. Now, first difference is, now these things are part of the effect system, so they're sort of tracked very precisely. It's not just some arguments floating around or fields or whatever. They are like for every single expression, not only do we know the type, we also know the effect. So we know exactly where these things are used. The second thing is the implementation is not passed around by, as an argument or putting it into a constructor or whatever, auto-wired. No, we use the stack. So that's what effect handlers are about. So imagine that you want to print to the screen, right? What's going to happen is that you say, I want to call the effect print to the screen, and then we're going to walk down the stack at runtime until we find a handler, exactly like with exceptions. The difference is, with an exception, when you hit the handler, well, then everything above is gone, right? And now you're trying to do some error handling and escape further out. But effect handlers are about also allowing you to resume. So when you hit that handler that is asking to write to the terminal, then you can decide, okay, I'm actually going to do the actual write to the terminal here. But you could also say, actually, I'm going to reinterpret the write to the terminal as logging to a file. And you can rethrow or that effect further down, so you can sort of have layers of handlers. So a nice thing you can do is that you can you can have some code that's written like there is a logger available. And then you can rewrite it to use a terminal. And then you can rewrite that to have handlers that use a database. And you can just stack these things on top of each other, and it will work out. OK, so I have this. This is the last overwhelming code slide. There's not much happening here, actually. There's some calls, and I see the time. There's not much happening here. There's a call to some logging. There is some HTTP request here. It can go wrong or not. You see, if it goes wrong, then we log some more. Otherwise, we get the response and we write it to a file. Writing can also go wrong or not. Now, of course, this shouldn't all be in main, right? But it's an example, right? You will divide it into smaller functions. This whole block actually has 3 effects. It has some file write with result, some HTTP result, and some logger. So down here, I install the handlers, and here I'm using some default handlers to say, well, I just want the effects to actually happen. But down here, I could also specify different implementations. So just to show an example, if I wanted to test that the HTTP part is always failing, I just install my own handler here, where I say, well, connection failed, and then I resume with that error. So now when I have this code, that call will hit here, and then resume with the error. Okay, so effects and handlers give us modularity, reusability, and testability. The modularity is that we know exactly how our program depends on the outside world, both indirect inputs and outputs. Things are reusable because we can just plug in different things, and it's more general than Java, where you have to sort of pass around some specific implementation of those things, because we can use the stack, so we can have different handlers at different levels. And this, of course, enables testability, because it gives us dependency injection and mocking for free. And of course, because of the effect system, there can be no lies. We know exactly all the effects there are. OK, so I wanted to change gears a little bit, actually completely, and talk a little bit about programming language design here towards the end. So basically, what I wanted to talk about is how we're designing Flix. And so, of course, as a language that embraces this effect-oriented paradigm, but also how can we actually do programming language design in a more structured way? And so one thing we've done that I've not seen many people do before is try to write down some principles and put them online. And these principles, what are they? They're like a social contract. So basically, we are trying to write down what you can expect from us and what we expect from you. So it's not really about good programming language design, because I think that's hard to define. It's more about systematic programming language design. So I'll just give you a taste. Skip this one. And say we've collected 41 of these principles. They fall into different categories. We give each a name and then a reasoning for it, as then a discussion about why it is like this, and then maybe a hypothesis. Okay, maybe looking at the example will be good. So one example is here about syntax, because people discuss syntax so much, and also in our group, everyone wants to discuss syntax, but it always ends up being like, well, that's just your opinion, right? And I have a different opinion, so how can we resolve this? So, just one example is here, we've decided that we should try to have, I use an academic term, term and type syntax should be the same, right? So for example, functions, we write them with like the single arrow, right? X goes to x plus 1. So then the type should be written like this. So it looks the same. Not all languages have this. Some languages, function types look different. Another example, if you write a tuple like this, well, then the type is written like this. So the syntax of expressions and syntax of types should sort of match. So that's one principle we have. Now, I'm not saying this is good or not. I'm just saying, this is something we want. And then now at least we can discuss what it is. Another example, this one is always controversial, so I hope you'll come up and object later. It's a very hard one. We have no warnings. Our compiler will never emit warnings. It only emits errors. So either something is absolutely permitted, and it will always work and be meaningful, or it's absolutely forbidden. And that's because, warnings, they can be turned off and not. And, when should you turn them on? When shouldn't you turn them off? And it's also like, what is the message here? Like, how serious is this? So this forces us to always decide whether something is completely banned or always permitted. And on the other hand, if it's always permitted, then there is nothing like, oh, you shouldn't do that. I mean, then it should have been an error. So that's another principle we have. More controversial ones. So this one is kind of cool because of the effect system, we are really good at finding dead code. So if you call some function and you were supposed to use the return result for something, or you have some expression that doesn't do anything, then the effect system says, hey, you're calling this thing. It doesn't seem to have any effects. In fact, we know for sure it doesn't have any effects. And you're not using the result. That's dead code. So what's happening? What do you mean? So that's not allowed. It's an error. We don't have variable shattering. We don't have unused declarations. Of course, this can be debated, but that's, that's how we design the language. And so we have a whole long list of these. We have the name and examples and rationale and so on. Not sure the example. And then we put them online on the website, so we can always consult them and discuss them. Yeah. So the message here is that I think this would be an interesting way for other people also to try to design programming languages. It would be cool if you could go to PHP or Java or Go or whatever, and they had a list of principles, and you can be like, aha, I understand exactly what that is, but I disagree with it, but at least I know what it is and what they're trying to do. Right? So that's what we're trying to do. Yeah, I think this I'll skip because of time. I just wanted to say there's more to Flix. We actually have some embedded logic programming in there. It's really cool. But you can check the slides later at the website. Right. So a major point here is that Flix is kind of a functional language, right? So you write functions, and functions call other functions. And you can do that in a functional way. So if you're like a functional programmer, right? Work with lists or whatever. However, Flix also gives you the opportunity to do it with those heap effects we saw, where you say, well, I'm going to do something a bit dirty here with lots of loops and mutation or whatever, but I'm going to confine myself to this scope. Now, in that scope, of course, you can call other functions too that do mutation. But you're saying, like, the memory I'm allocating now to work on, at the end of this scope, it's going to disappear. And because it's going to disappear, this function will actually be pure or only have other effects that were somehow left over. So that means you can be a functional programmer, but write in an imperative style. And the last thing which I didn't show is that you can also write functions actually by giving a small logic program. So you write functions, but you're free to inside choose a paradigm that fits better with what you're doing. So to return to this point at the end, we're really trying to build something real. So I'm just going to take you through some slides of what we've done. Of course, we have a website with a front page that tries to show like a lot of flavor of the language, flix.dev, so you can go there. It tells you how to get started. There's some small videos even. There is an online playground inspired by the Rust playground where you can write Flix programs. It runs on a server, so please don't mind Bitcoin. Although it would be cool if you write like a Bitcoin miner using effects in Flix. So I'm kind of torn between that. Maybe you write it and then you send it and I let it run for a while. We spent really a lot of effort on building great VS Code and LSP tooling. In fact, I would argue that, so I think that tooling is like 10 to 15,000 lines of code, last I checked, which is bigger than many sort of prototype things. And this includes like very sophisticated autocomplete, which has been like a total nightmare to implement. But actually, it's also really fun. So there's both like specific VS Code support and also sort of generic LSP support. Without going into detail, it turns out that the LSP story is not as true as you would hope it is. So, there's sort of more things you can do if you work directly with Microsoft, let's say. So that's there. And there is a book, online documentation. It's about 150 pages, 200 pages, basically describing all the features of the language, lots of examples and so on. It's describing the effect system in particular. There's API documentation like Javadoc or whatever. The nice thing about being a researcher is that everything is open source and expected to be. So everything we do, research, implementation, all this is available open source. Our papers also, all those things are available. This is just a rehash of our, pretty much everything of LSP. Another thing is like we really focused on and know how important, some people were saying like new languages let's put it gently and say it's very difficult for a new language to be successful, right? And so I think part of that is that you need to have excellent tooling. So that's really something we are focused on. So as another example of that is the same compiler is used for all the tooling that is used for any IDE support or everything like that. It's one code base. And so, for example, you don't have this problem that was in many languages where there are two compilers and then they somehow don't agree. Like, the IDE says here's an error, but then you run the compiler and the error is not there, or vice versa. So they're always in agreement because there's only one. And our compiler has like a pretty modern architecture, I would say. So it's built from the beginning to be, not from the beginning, but it's over time we have made it resilient, incremental, and parallel. There are actually many compilers today that are not parallel. They might be parallel like at the file level, or you can invoke like multiple processes, but sort of really deep inside the compiler, they're not parallel, but ours is. So here's some numbers. And so this is what you need for, when you're typing in the IDE, right? And this number is without incremental compilation. So you have to type pretty fast, before you have to wait, or you get responses pretty quickly. To wrap up, also just to show, so it's, on the research side, there's also collaboration with other universities, Copenhagen University, University of Tübingen, Waterloo. We just passed 10,000 tickets and pull requests, so it's also kind of big in that way. We have 250,000 lines of code, so it's like a real thing. Now, of course, on the research side, there are several new ideas in Flix, mostly related to the effect system. So we published research papers about those. Those papers, of course, more technical, but I always try to write an introduction and a motivation section, so the first couple of pages, that are sort of broadly accessible. So if you're interested, you can also go and find these papers. But separately from that, the online documentation really also just explains the language to programmers. But this is if you want to go deep and understand some of the technical challenges. Okay. So in summary, so I think effect-oriented programming will play some kind of role in the next 10 years. It's very hard to know what shape it will have. It's also possible that it will, like many other features, make its way via the back door, right? So Scala is adding something called capabilities, which is sort of related to effects. I can imagine Kotlin or other languages sort of adapting things towards that direction. There's also Rust, also interested in effects. Swift is also sort of. So I think, the other option is that sort of you get, like Java, C#, they are accruing all the good ideas, right? But always in a handicapped version. So maybe, you will learn about effects in a handicapped way. There are also some people trying to do it with libraries, even for JavaScript, right? Successfully. But then, if you don't have the effects system, you can have effects and handlers and those kind of things without the effects system, then you just lose all the guarantees, right? So it's like, you get more expressive power, like in JavaScript, you can do whatever you want, but you also don't know anything anymore about, what can happen. I also think effects could have a huge role to play in security, because really, if you're running someone else's code, at the end of the day, you need to know what it's doing. Are you going to read all that code? No. So then you need an effect system with the type system to tell you, well, this is what comes in, this is what goes out, and this is what it does to your machine. Okay, so our contribution here is Flix, which is a new programming language. So yes, it's a reset, start from scratch. We have to re-implement everything in Flix, maybe. Actually, I should point out we run on the JVM, and we have Java interoperability. You can read about it. So okay, so maybe we don't have to re-implement everything. And it's a real effort at building a real thing. We're moving towards version 1, so now would be a really good time for you to go and play with all these things. And this is the website. And I'm out of time, so thank you for your attention. If there are common questions, we can take one or two, otherwise I'll stick around up here. We can also discuss like if new languages have a chance. Oh, question. Okay, yeah. Sorry.
Design principles. Oh, sorry. The design principles, are they enforced somehow to the developer? And if so, how?
If they are what, sorry?
Enforced to the developer. And if so, how?
You mean the Flix developers or you as a Flix programmer?
The developers that use
No, it's
Flix.
more like a social agreement, right? It's like, for example, this one, right? Then someone comes along and says, oh, we want to add this thing, this is not good, it should be a warning. And then you say, well, there are no warnings in Flix. We've agreed on that. So either we have to have a big discussion, sort of in the team, and abandon this principle. We have a list of abandoned principles too. 2 principles have been abandoned. Or you have to say, well, I mean, we agreed for really good reasons that Flix would not have warnings. And so you're proposing to add something that's a warning, so now you have to decide really, should it be an error, which is a much stronger statement, or should it be, should it not be there at all? Another thing is like someone says, oh, I want to add some syntax, and then, if there's some expressions and some types at the same time, then the syntax has to be somehow consistent. But these things are, of course, not enforced. I mean, they are just choices. They are just choices that we've just bothered to write these things down together with some discussion about it. So one thing new languages, I think, can agree on is like they say like, we don't have null, or they say we have like a nullable type system. That could also be a principle. That's sort of the closest I've heard from other languages about some principles they have. But we have like 40 of these. And so it's really like when something is changing in the language or someone wants to add something, then we can use this as a fallback to say like we earlier agreed that we wouldn't do this or that we would do it this way.
Like design choices.
They're design choices, yeah. Yeah. Sort of general design choices, right? Yeah.
But when you agree on one of those and you adopt it,
Yeah.
you eventually enforce it through the language, right? I mean,
The ones that relate to features like this one, yeah, variable shadowing is enforced, right? So we have another principle that is called like error messages should be friendly. So I'll give you an example. Instead of saying illegal foo, because why are you breaking the law? It should say unexpected foo. Okay, now I'm not kidding. There's even been research on this, not my research, but there's been some research about how to phrase errors. And so we have a principle that says that the language should be friendly. Now I don't know how to enforce that. That's just, every time someone is changing the text in an error message, we check that people don't write sort of bad words, but try to phrase it a little bit more positive. For example, unexpected is better than illegal. Another example is we try to say the word that you have in mind, let's say it was student again, should occur early in the error message. So instead of on this line, on blah, 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 this type, unexpected student, it should say student unexpected here. Because then when you're reading, you see this word student that relates to your program earlier than at some end of some long sentence. That's another principle, moving the, what we call the subject to the beginning. Yeah.
Yeah, one practical question about any build tools or support for build tools. The second, a more broad question, how Flix differs, maybe it's a long discussion, but how it differs from other effect systems like in Scala effects, catch effects or Zio. Or,
yeah, okay. I actually think there are 3 questions in there. Is it okay if I try to answer them quickly? So, look, it has to be kind of a reset, because there's no way to, maybe someone could refactor Java to have effects, but then they would have to add it everywhere, right? And when we call a Java method, we don't know what it can do, so we have to say it can do anything, right? So in Flix, when you interrupt with Java, there are 3 levels actually. So you can write, and Flix has a package manager and a package ecosystem. So you can write pure Flix code, and then when you depend on it, you've written a package, I depend on it, I can say, okay, I expect it to be pure Flix code, then all the guarantees hold. Then you can write a package that says, okay, I'm going to use Flix and the Java standard library. And then when you make a dependency, you say, okay, I allow you to use the Java standard library. Then we have some support for that. And that means that now if you trust us and you trust the Java developers to not do something crazy in the library, we still have good guarantees. And there's the third thing where you could say, actually I want to depend on some of my own Java code or some Maven package. You can depend on a Maven package. But then you're saying like, okay, now I'm really in a dangerous world because I'm just promising that I don't have this effect now. Now the signatures have become like in TypeScript or other languages where they're more sort of aspirational. They're not hard guarantees anymore. So then we can sort of envision that, the person who's writing some package like, here's how you color something in the terminal. That could be like a pure Flix package. And it shouldn't really have any side effects, right? It shouldn't depend on the file system to color some string, right? On the other hand, if you need a web server, right, and you want to use light HTTPD or whatever, then yeah, okay, you say, okay, you can do that and you have all the effects, and I really have to trust the developers now of this Flix package that relies on light HTTP. That was the thing with that, the package thing. Then I think you asked about Zio and Scala effect and all these things. So yeah, so those are examples of things coming in via the back door. So these are library attempts to give some of the benefits of effect handlers. These are some libraries for Scala. There's also some for JavaScript and other things. These libraries are popping up. So they give you kind of the expressive power, but they don't give you the guarantees because they're not part of the language. Would be my short answer. I forgot what the third question was. Yeah, it's okay, yeah. Okay, I'll stick around somewhere. You can come to me with more comments.